Okay, we have a problem here where someone is throwing a baseball over a fence, and the problem is we don't know the initial velocity of the baseball. So on the left, you see this v. That's the velocity of the baseball, so it's a vector. And so we don't know what it is, but we do know it was thrown at an angle of 56 degrees with the horizon, and it's up on, let's say, a pedestal of 1.6 meters. So this baseball is being thrown 1.6 meters above the ground. It's being thrown at 56 degrees from the horizon, but with an unknown velocity. The problem is it has to move 14 meters horizontally, and it also has to go just over the fence, and the fence is 5 meters high. So what's like the minimum velocity that we could have that would satisfy the constraints of both A, going 14 meters and in X, and 5 meters in Y? And once again, it's the minimum velocity. Obviously you could say, it could go 1 billion meters per second, but we want the minimum. Okay, so how are we going to do this? Well, what we're going to do is we're going to break this problem down. So we're not going to use normal equations of motions. We're just going to use, integration and differentiation, i.e. calculus, to just solve this problem from first principles, okay? So what we're going to do is I'm going to draw a graph of the velocity in the x direction against time, and the velocity in y also against time. Okay. So up here you can see that the velocity is a vector, and it's 56 degrees. So what is the x component and the y component? What does that look like? Well, the x is just v, whatever my velocity is, times the cosine of 56 degrees. And the up and down, or the y, is v times sine 56 degrees, okay? So do we know what v is? No, we don't know what v is. So what we're going to do is here on the graph then, on vx, what is the initial velocity in x? Well, it's just v cosine 56. And then over here on y, it's v sine 56, okay? Now, in the x direction, is there a force that is, once the ball is released, is there a force that's pulling the ball, is there a force that's making the ball increase or decrease its velocity in x? No, it's not. So the x velocity actually keeps going until, it hits the ground or something. But until then, the velocity doesn't change, okay? Until it stops. Okay, well, and we'll just call that, t or whatever. So at some time it's going to stop. But until then, it's going to keep going. Now, what about the y? What does the y look like? So it's initially at some positive. It has some positive velocity, right? Because it's going up. You can see the arrow right there. It's going up. So the velocity is positive. But then what happens after that? Well, due to gravity is going to pull on the ball, right? And so the gravity pulls at 9.8 meters per second, right? So what we're going to do is we're going to create a slope here that is the acceleration slope. And so what this is that this slope is the slope due to acceleration. So the slope here is actually negative 9.8 t, okay? So that's the slope of this line, because once again, gravity is pulling it down at 9.8 meters per second, and that's what this t means, per second. But it has a y-intercept, right? So the y-intercept, of course, is v sine 56. So the equation of this line is negative 9.8 t plus v sine 56. Great. And the other one, just to be certain about it or specific, is the equation of this line on the vx is really just v cosine 56. It doesn't change, right? It's constant. All right, so that's cool. So that's nice. But what I want to do is I want to figure out two constraints. What is the velocity of this ball but it has to move, what's the minimum velocity it can be, but it has to achieve both it has to go 5 meters high, and it has to go 14 meters wide, or in x. So what we can do, though, is instead of doing these velocity graphs, which are nice, we can instead create a position graphs. So position in x and position in y. So I'm going to create an r x for position in x and ry for the position in y. Obviously, it's also relative to time. Okay, so let's do the x first. So in order to find the position in x, the function for Rx, what I need to do is take the velocity of x, that function, the v cosine 56, and integrate it, right? So if you integrate v cosine 56, well, you're just going to end up with, first of all, actually before I do that, I want to know in Rx, what is the initial position in x? So the initial position in x, if this is our origin, right here, if that's our origin, which I'm going to specify, obviously you could put your origin wherever you want, but I'm going to specify that's my origin. So if that's my origin, then where is my x at? Well, it's at 0, right? So I'm going to say here. So that is my initial position in x. Great. Now that I have my initial position, now I can create the function from that. And so once again, we're going to take v cosine 56 and we're just going to integrate it. And so if you integrate that, then you're going to end up with a linear function that looks, sort of like that. And that's going to look like v cosine 56 t, because it's a function in time, plus 0, right? And then the 0, of course, is the y-intercept. You don't really have to write plus 0, but I'm just writing here the plus 0 is the y-intercept. So that's what this function looks like. V cosine 56 times t. Great. So what does y look like? The y position. Well, what we have to do is we have to figure out what is our initial y. So if you look up at the plot at the upper left, you can see that the y is up. When I throw the ball, it's 1.6 meters up. So we can start, like here, and write 1.6 meters. Okay. And then what is it going to look like? What does the graph look like? Well, it's a parabola, right? It looks sort of like that. Okay. And this is coming from what we're going to do. We're going to take this guy and we're going to integrate him. Right, we're going to integrate him as well too. So this was integrated, right? The integral. This was also integrated. Okay. If you integrate a negative 9.8 t plus v sine 56, what do you get? Well, you get negative 4.8 t squared plus v sine 56. Right. So that's what you have. But then you have to put on your initial conditions, which is 1.6 plus 1.6. And there you go. So now we have two functions. I'm just going to highlight them. We have this function here. The 0 doesn't really count. And then we have this function here. So we have two functions. And what I want to know is the function on the right, the negative 4.8t, it has to go up 5 meters, and the other function has to go over 14 meters. Okay. So I want to know where this function here, the negative 4.8t squared plus v sine 56 plus 1.6, where does that, maybe I'll just write it down. Negative 4.8 t squared plus v sine 56 plus 1.6. Where does it equal 5? So 5 is right here. 5 is right here. Okay. And so what I'm looking for is either this point or this point. So I'm trying to. So where is that? Where does that intersect? Where does the function negative 4.8 t squared plus v sine 56 plus 1.6? Where does that intersect the line 5? So we have two lines, right? We have the curved line and we have the y equals 5 line. So we have those two lines, and I want to find out where those two lines intersect. So this is an equation. Now the problem with this equation is that there are two unknowns. The t is an unknown and the v is an unknown. Okay, so I have one equation with two unknowns. You can't solve that, right? But what I can do is I can go over here on the left and I can say, well, this thing has to go, I'll extend it up a little bit. It has to go 14 meters, right? 14 meters. And so if I put a line right here, I know it looks kind of messy. It's right here. So over here I have two functions, the v cosine 56t, and then I also have 14. So where do those two functions intersect? So let's write that down. So if you write v cosine 56 degrees times t equals 14. Okay? So I have two functions and I have two unknowns, the t and the v. And if you solve this, you actually will get it's just a system of equations, right? If you solve this, you end up getting v equals 13.30. This is in meters per second, and the time is 1.88 seconds, 88 seconds. Okay, so if you solve this system of equations, it'll show you that the velocity needs to be 13.30 meters per second. Now the time is actually, when you say time, what time is this? It actually the 1.88 seconds is just here. So right here is t equals 1.88 seconds. So at 1.88 seconds, if the ball was thrown at t equals 1.88 seconds, if the ball was thrown at 13.30 meters per second, it will have traveled 14 meters in the x direction and 5 meters in the y direction. Both of those constraints will be satisfied. Cool. Now you may want to know, where did the ball land? So the ball did make it over the fence, but where did it actually land? And so this x on my plot at the top, or my drawing at the top, my x, where did it actually land? Okay, so in order to know where it landed at, let's go back to this r equals y. So this ry plot. So instead of saying this negative 4.8 t squared plus v sine 56 t. Oh, sorry, this is it. There's a t here. Yes, sorry. Yep, I missed that. This is a t. Dude, right there. That's a t. So the negative 4.8 t squared plus v sine 56 t plus 1.6 equals 5. That's where the curved line meets the 5 line, okay? But now I want to know, where does it equal the 0 line? The 0 is 0 in y. Where is 0 in y? That's the ground, right? So that's this. So where do they two meet? Let's just do this right here. That's this point right here. Where do they meet? Which is right there. So I have to solve the equation negative 4.8 t squared plus v sine 56 t plus 1.6. Where does it equal 0? Where do those two functions intersect? Now remember, v here in this case, v is 13.30 because we already figured that out. And so if you do that, you'll end up with t equals 2.387 seconds. 2.387. So that's this point right here. T equals 2.387. So at 2.387 seconds, the ball actually hits the ground. And so if I know that, then I can substitute this t in right here. I can substitute it in right here. And this v, of course, is 13.30, right? So this 13.30, this is 13.30 meters per second. So I have 13.30 times cosine 56 times t, which is 2.387 seconds. And if I do that, then the total distance in the x is 17.75 meters. So here it is over here. This is 17, x is equal to 17.75 meters. Okay? And so that's it. So to recap, if someone throws a ball at a velocity of 13.30 meters per second at 56 degrees with the horizontal, up, and he's standing up 1.6 meters, and throws that ball will just go over a fence that is 5 meters high, that is 14 meters away, and then it'll finally land 2.387 seconds. This is in seconds. It will land 2.387 seconds later, and it'll finally land at 17.75 seconds. 17.75 meters. So once again, I solved this problem. You could have used the equations of motion, right? That you would find in any physics textbook. But here I'm just trying to show you that you don't necessarily need them. You can just, from first principles, figure out, okay, here's the setup for the problem, and I'm just going to use some graphs and basic integration, differentiation, i.e. calculus, maybe some geometry, some algebra. And I'll use those basic math techniques to solve the problem. Instead of someone giving me a bunch of equations, I can just solve it directly. And I find this way is a useful way to figure out how stuff like really works instead of just plugging in numbers blindly. So that's it. Hope you enjoyed it, and see you later.